Hello guys, welcome back to my YouTube channel Data Scout. In our previous video, we have seen how Pearson correlation coefficient solves the limitation of covariance. So we have seen Pearson correlation, which in short we say PCC, solve the limitations of covariance. So similar to covariance, even PCC has some limitations. PCC also has limitation. Like Pearson correlation coefficient doesn't work well with non-linear dataset. So we have seen how PCC works very well if the datasets are linear. So if this dataset, if I say this is a linear dataset, so PCC works very well with this kind of a dataset. It will give what it will give. It will give a perfect -1. X is increasing, Y is decreasing, dataset falls in a linear line, so PCC will become -1. And we know the range of PCC. What is the range of PCC? Let me just put it here. -1 to, if I just denote PCC as P here, +1. Alright? This is what the range of PCC. So let us recall first how this range play out. We will take the help from Wikipedia, which is a great source of information. So let's give a shout out to Wikipedia for this. Let's see this Wikipedia page here. Let's see this example here. We have already seen this kind of examples where the data sets falls in a linear fashion and we see it's a decreasing. So Y is, let's say this is Y, this is X, and we know Y is decreasing, X is increasing here. So data sets are falling in a linear line. So P equal to -1. And we know here it's little bit scattered from, if we try to draw this line, it's giving a range of -1 to 0. So let's see the examples of this kind of nature, of this kind, where it's not falling, the data sets are not falling on a linear line. So let's see the examples of this nature. We are very good here. The data sets, if you see here, the data sets are falling in a linear line. So it's giving +1 exactly, and this will become P equal to 0. So let's see these examples. If I try to draw this as a plot, if I say this is an x-axis and this is an y-axis, if x is increasing and y is increasing and the dataset perfectly fall in one line, you can see the datasets are nearly perfectly falling in one line. So the PCC, or if I just say P is equal to 1, which is written here. Let's see this example here. Let's see the data set here, which is, if we see here, X is increasing and Y is increasing, but the data set is not perfectly in a linear fashion. You can see, if I try to draw a linear line, yes, it is drawing a linear line. We can see most of the data falls in linear line. But if you see here, the data sets are flattering, right? Some data sets are scattered near the linear line. So in that kind of scenario, our P value, which is PCC, will equal to 0.8. If you see this example here, if I try to draw a single linear line, yes, we are able to see there is a relation, or we are able to draw a single linear line. In this data sets, looks much more flatter than the previous one, this one. So in this kind of scenario, the P value will become 0.4. So with this plot, if I try to see, the data sets are literally in a circle way, right? If I try to draw a linear shape, it doesn't matter, right? We can see here it's a circle. So because of that, the P value which is given is 0. So similar to this, if we try to see here, if we try to plot this data set, X is increasing, and if we see the Y value is decreasing, and the data sets are flatter, right? If you see here also the data set is decreasing, but because it falls in a linear line, the P value is -1. And here, similar to this, the value comes from the range of -1 to 0. So this one, because it's flatter, it comes as -0.4. So the P value becomes -0.4 because it's much more flatter compared to this. If you see this here, where the data set is still flatter, but it's near to that linear line. So it's much more precise or much more related compared to this. That's why we are near to 0. This value is we consider as near to 0, right? That's why this is P equal to 0.8. So let's see, we have seen already this -1. So let us leave that out. Let's see which is important. Let's see this row. Let's see. Let me change my color of the pen. Let me just take a red. Let me use it. From this kind of plot, where if I try to do a plot here, let me just do plot for all of this. If you see this kind of plots, we can see that all the values is given as 1, right? But if you see the slope of this line, linear line, can you see? If you see here, if I just denote this angle as theta, we can see theta, if I just say it's nearly to 60 degree. I'm not saying exactly, but yes, approximately it's just 60 degree. But the p-value is 1. Why? Because it's this line, this slope, this data set falls in a linear line. Similar to this, if I just try to compare here, this theta may be at 45. So this theta is less than the previous one. But because this data set falls in a single line, the p-value is still 1. And similar to this, you can see here also, this theta is much more lesser than the previous one, but still the value is 1 because this data set which you can see here, it falls in a linear line. So here I can conclude, we can say that PCC doesn't bother about, or if I say Pearson correlation coefficient doesn't bother about the angle, the theta, it only bothers about the linearity, right? If you see here, if I just try to see here, it's giving a -1. It doesn't bother about any angle. It is just bothered about the linearity. If there is perfectly linear, you can see here, right? The data set follows in a perfect linear fashion, which is a downtrend, right? It's a downtrend. So it's a -1. It was an uptrend. You can see here, the data sets are going up, X is increasing, Y is increasing. That's why it's a positive one. So let's see, we have already said in this video, earlier to this video, that the limitation of Pearson correlation coefficient is handling the non-linear data set. So in today's video, we will focus about the non-linearity of data sets, which can be handled with Spearman correlation coefficient. So you can just see guys here, here the data sets are not in linear fashion like this. The data sets are non-linear, right? These are all non-linear data sets. But if I just say there is some meaning where at this level the values are coming down and after post this it's going up. So there are some certain relationship with the data set, but it's not linear. This kind of data set we say a non-linear data set. So we will try to see the limitation of PCC, which is it's not able to handle this kind of data sets and it's all giving 0, 0, 0. So we'll try to handle this with Spearman correlation coefficient. So let us see how we can handle the limitation of PCC by Spearman rank correlation coefficient. Let's see the mathematical connotation of Spearman correlation coefficient. Let's see this mathematical connotation of Spearman rank correlation coefficient. So if we say Spearman rank correlation coefficient equal to nothing but Pearson correlation coefficient with rank of X and Y. In Spearman rank correlation coefficient, what we are trying to achieve with Pearson correlation coefficient, we are trying to give the rank. For Pearson, we always used to write Pearson of X and Y, right? But here what we will say in Spearman rank correlation coefficient, let me just put like this, equal to Pearson of rank of X, comma, rank of Y. Let's again go to a Wikipedia page, which is a great source as I have told. So let us use the Wikipedia page. Let's go. So let's see this formula here. If you see in this formula, so if you see the difference in Spearman correlation coefficient, Instead of covariance of x and y, in Spearman correlation coefficient, we are using rank of x, covariance of rank of x, rank of y. If you see standard deviation of rank of x, standard deviation of rank of y. And this is the formulation. This is the formula which we are going to use to calculate our Spearman correlation coefficient. So guys, let me come to this example here. We are trying to see the correlation between, if I see the correlation between the IQ and the hours of TV per week a user watches, right? So we are trying to see. So let's see, we are giving this 106 IQ level of a person who watches only 7 hours per week. We will not consider the variable. Instead of variable, we'll consider the rank of variable, right? Rank of variable. So if I just say this is my x and this is my y, so we are not going to consider this variable. Instead of this, we are going to consider the rank of it. Similar to this, similar in this also, in y, what we are trying to do, we are trying to consider the rank of y instead of y. So let's come down. Let's see. Let me just rub it and let's come down. Let's see these steps, how we are performing, right? So let's start here with the steps. So Wikipedia has mentioned these steps and we are trying to follow this step. Let's follow this step diligently. So what is the first step which is asking? Let's sort the data by the first column of xi, create a new column small xi and assign the rank values. So if we see here, let's say this is our x variable and these are the values. So if you see here, with this example, this is unsorted, right? Unsorted. And if you see this, we have sorted this data, right? 86, 97, 99, sorted in its ascending orders. And it has written we have to create a rank with the new variable xi. So this is the rank of xi. And if you see here, because we have sorted, we can easily find out the rank. So 86 will be the first rank. Again, I am saying guys, because we are going to consider the rank instead of the variable, that's why we are converting. We have completed this first step now. Let's understand the next step. So in the next, sort the data by second column yi, create a column yi similarly and assign the rank variables. So here, if you see, it's not sorted, but if I try to rank, if I try to find the variables, right? If I just see this variable, which is the smallest value, guys? Which is the smallest value? If I see below 10 is this, and I know 2 is the smallest and 6 comes after that. So if I just say this should be 1 and this should be 2, so let me find there. Can you see this is the y variable? And if I see the rank of this variable, rank of y is 1 and we know 6 comes here and the rank is 2. So here also what we have done, we have created a new variable rank of yi and we have given the rank of y variable. Create a fifth column. So we have already have x, y, 2 columns. Then we have created rank of xy and rank of yi, which makes 4 columns. Now we will have to create fifth column di to hold the differences between the 2 rank columns. So di we will create and we will create the difference. So 1 minus 1 is nothing but 0. So 2 minus 6 is nothing but minus 4. So we have created this new fifth column. So let's see the final steps, which is fourth. Create one final column di squared to hold the value of column di. So let's see this here. If you see this here, it's saying we have to do a square. So we see this di value, we'll just square it. So 0 squared is 0. Minus 4 squared is nothing but 16. Guys, we have created this. We have followed these steps and we have created all the columns which is required. Now let's see this formula. Let me just write here in empty space. So let's understand each term one by one. So what it's saying, it's having summation of di squared and n, right? Number of items, number of elements or items in the data set. So let me count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 elements in this data set. So let's say n equal to 10. And let's see this summation. So this is the di square column. So the summation of this column, the value comes at 194, which is written here. So if I just say di square value is nothing but 194. So we have got this di square which is required in this formula. If I just say here, and we have this n. So let me just derive this formula. 1 minus 6 into 194 divided by n. N is what? 10, and then n square. So let's say 10 square minus 1. So if we do this, the value comes, which is nothing but minus 0.175757. I have used calculator to calculate this, but yeah, this is what the value comes, and this is what has been written here. So let's not come here the p values and this t distribution, which we are going to see in our next videos. The values are much more precise in Spearman rank correlation coefficient compared to PCC. So now we have seen the values comes minus 1.75. So see, it's saying that the value is close to 0, shows that correlation between IQ and hours spent watching TV is very low. Although the negative value suggests that the longer the time spent watching television, lower is the IQ. With the help of Wikipedia, let's try to understand this diagram. So in this, if you see in this graph, or if I say in this plot, if you see x is increasing, and similar to x increasing, even y value is increasing. So we have seen here y is increasing and x is increasing, right? If I try to draw a linear line, something like this will be a linear fit. But all the data are falling in a linear line? No. So p equal to 1, not possible. You can see here, we have this data set here, but there are few outliers here. Can you see these outliers? So Pearson correlation coefficient doesn't work well with the outliers. But whereas Spearman rank correlation coefficient works well with the outliers. So we can see, because Pearson is not able to treat this outlier, that's why the values are less than Spearman rank correlation coefficient. Spearman rank correlation coefficient handles the outlier properly. Spearman is much more robust to handle these outliers. So hope you like this video. So if you like the video, press the like button, hit the subscribe button, so that whenever I come up with the new videos, you will get the notification of those videos. So guys, if you have any suggestions or you have any comments, do comment. I'll try to reply each and every one of you. Thanks guys. Thanks everyone for watching this video.